At the core of modern civilization lies a paradox. Humanity is surrounded by an infinite ocean of energy, sunlight, yet continues to burn finite, polluting fuels buried deep in the earth. The bridge between these worlds is a deceptively simple device, the solar cell. But beneath the sleek panels that glisten on rooftops and satellites lies a story not of engineering alone, but of quantum mechanics, a story of photons, electrons, and the invisible dance of energy conversion that powers our future. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. Light is not merely illumination. It is a stream of quantized energy packets known as photons, each carrying a discrete amount of energy proportional to its frequency, as described by E equals hf, Planck's revolutionary equation. When a photon collides with matter, it does not spread its energy gradually. It delivers a single quantum punch. And that singular impact is what makes the solar cell possible. The birth of the solar cell begins with Albert Einstein's 1905 photoelectric effect, a discovery that earned him the Nobel Prize. He showed that when photons strike a metal surface, they can eject electrons if the photon's energy exceeds the metal's work function. This was the first experimental confirmation that light behaves not just as a wave, but as a particle, a quantum entity capable of transferring energy in precise amounts. It was this realization that turned sunlight from a passive glow into an engine of electrons. The early 20th century physicists laid the groundwork, but it wasn't until 1954, when scientists at Bell Laboratories combined silicon wafers and the photoelectric effect, that the first practical photovoltaic cell was born. A solar cell, in essence, is a quantum machine. It absorbs photons and frees electrons, but only if those photons carry just the right amount of energy. Too little, and the electron stays bound. Too much, and the excess energy is lost as heat. This delicate balance, dictated by the band gap of the material, is the quantum heartbeat of every solar panel. Inside a semiconductor such as silicon, electrons occupy specific energy bands. The valence band holds electrons bound to atoms. The conduction band is where they are free to move. Between them lies the band gap, the forbidden zone. When a photon hits the material, its energy must be just enough to elevate an electron across this gap. That quantum jump transforms a bound electron into a free charge carrier, ready to flow as electric current. The entire efficiency of a solar cell depends on this quantum threshold. To direct the flow of freed electrons, solar cells are built with p-n junctions, a boundary between p-type, positive, with holes, and n-type, negative, with extra electrons, semiconductor layers. This junction creates an internal electric field that separates electrons and holes once they are created by sunlight. It is this invisible field, this silent quantum traffic controller, that turns random photon strikes into organized, usable electricity. But the story doesn't end with freeing electrons. Not every photon is absorbed, and not every excited electron makes it to the circuit. Some recombine with holes, releasing heat instead of current. Others are lost due to reflection or material imperfections. The proportion of photons successfully converted into electrons defines a solar cell's quantum efficiency. Scientists continue to chase the elusive goal of minimizing these losses, an engineering challenge rooted directly in quantum mechanics. Recent advances have taken the quantum nature of solar cells even further. Quantum dots, tiny semiconductor particles just a few nanometers across, can be engineered to have precise band gaps simply by changing their size. Smaller dots absorb higher energy photons, larger dots absorb lower energy ones. This tunability allows multi-layered cells that can capture more of the solar spectrum, surpassing the theoretical Shockley-Queisser limit of traditional silicon cells. In other words, we are designing sunlight absorbers atom by atom. Another breakthrough material, Perovskite, has revolutionized the field with its ability to be printed cheaply while achieving high efficiencies. Perovskites combine the classical principles of semiconductors with flexible quantum behaviors. Electrons move freely through their lattice, allowing efficient charge transport with minimal loss. They may one day replace silicon altogether or work in tandem as tandem cells, where different materials harvest different wavelengths of light in perfect quantum cooperation. In the smallest scales, new effects emerge. Quantum tunneling, where electrons can pass through barriers once thought impenetrable, and plasmonic effects, where light couples to collective oscillations of electrons in metallic nanoparticles. These effects can enhance light absorption, guiding photons into nanoscale traps that keep them bouncing until they surrender their energy. Such architectures demonstrate the next frontier: quantum-engineered solar cells, optimized not only through materials science, but through manipulation of the fundamental laws of quantum physics. As the world faces accelerating climate change, the importance of this technology transcends physics. Solar cells embody the shift from extraction to conversion, from taking to transforming. Each panel represents an elegant intersection of quantum science and ecological responsibility, a device that turns light, the most abundant natural resource, into sustainable power. In the language of the universe, its energy transmuted into civilization. Despite tremendous progress, solar efficiency remains bounded by the Shockley-Kieser limit, around 33% for single-junction cells. To surpass it, researchers explore multi-junction cells, hot carrier capture, and even quantum coherence, where wave-like interactions between electrons can preserve energy longer than previously possible. At the frontier, some physicists envision quantum photovoltaic systems that mimic the light harvesting mechanisms found in photosynthetic bacteria, organisms that have mastered solar efficiency through billions of years of evolution. Solar cells are more than devices. They are embodiments of one of physics' greatest triumphs: the harnessing of quantum phenomena for practical, planetary benefit. Every watt of sunlight converted to electricity is a small victory of human ingenuity over entropy. The more we understand the quantum realm, the closer we move to a sustainable civilization powered by the same light that gave life to Earth. From Einstein's photoelectric insight to today's quantum dot revolution, the journey of solar cells mirrors humanity's greatest quest to understand and harness the laws of nature. In every photon absorbed and every electron freed lies the promise of a cleaner, brighter world where quantum mechanics and sunlight illuminate the same horizon. If you found this content helpful, don't forget to like, subscribe, and share. Leave me a comment. Let me know what you think about solar cells and the future of sustainable energy. Join me next time for another deep dive into the strange and unusual world of quantum physics.